Hello, good morning to one and all. I am Dr. K. Srinivasarao, Professor and Head of Microelectronic Research Group, VLSI Specialization and Department of Electronics and Communication Engineering. So today I am going to discuss about the topic from the course, the core course of VLSI Specialization. The name of the course is VLSI Design and the course code is 21EC2211R. So the content of my particular this video lecturing is from CO1. So we have CO1, CO2, CO3 and CO4 in this course. So I am going to discuss the three topics from CO1. The first topic is on introduction to Mos transistor and its description. Second topic is Mos transistor device characteristics, and the third one is the fabrication process of the CMOS technology and also Mos transistors. So this is the syllabus of the 4 COs, CO1, CO2, CO3 and CO4. So these are the textbooks are referred for the CO1 as well as for the other COs also. The famous textbook is the Douglas A. Pucknell Basic VLSI Design, PHI Publishers, 3rd edition from 2011. And also Neil Westy is another textbook which is referring for the second CO and third CO, that is the CMOS VLSI Design, Circuits and System Perspectives. The publishers are the Pearson. And the some more can is another textbook which is offered third CO and fourth CO for the CMOS digital integrated circuit analysis. So there are some two reference textbooks and also the MOOCs course and web links are there. So as far as the CO1 is concerned, the topic is introduction to the Mos transistor technology. So let us discuss about how the Mos transistor has come into the picture of the electronics, particularly in VLSI, and after that we will discuss about the structure of Mos transistor, and then we will discuss about its characteristics and also the fabrication process flow. So as we all know that day by day our daily life is becoming so significant and so smooth because of the electronics engineering technology, and because of this we have so many of smart devices in our professional life and also workspace and also leisure activities and so many things. And there was a revolutionary happened in the electronics way back in 1947. In fact, from that few decades has been developed a lot of devices in electronics. So today electronics is characterized and tested by the based on the device of its reliability, based on device of its low power dissipations and extremely low weight, low volume and low cost point of view. So in this point of view, how the devices are developed and designed and manufactured in VLSI specializations towards to the different applications. So already the electronics given a lot of importance to the integrated circuits. Because of the integrated circuits, we made possible for the design of powerful and flexible number of the processors today we used in our regular activities of our systems, and they are very highly intelligent and adaptable devices for the user. And also there are some memory devices are there in this aspect which will have the same processors together with wide range of the logic and analog integrated circuitry point of view. So the capability and extensive applications of all these devices which will be provide a very good applications to the users in especially in the electronics. So that revolutionary advances in the technology, which means that they will run their codes, I mean these particular codes, and also the potential of these particular codes to the future development of the existing of the devices. So let us give a briefing about how this Mos transistor has come into the picture. In 1950s, electronic active device technology was dominated that time by the vacuum tubes. Therefore there was a miniaturization concept has been done, and circuit integration is just taken place at that time. So the technology, it was not land itself to the up to the mark of the miniaturizations to accept today what we have, and the majority of the present day of electronics is the result of the invention of the transistor in 1947 after that. So the invention of this transistor was developed by the three great peoples, William Shockley, Watt and John Burden from the Bell Telephone Laboratories for the this given a way path to the development of the integrated circuits, and the first very integrated circuit is begin in 1960s, and since that time there was 4 generations of ICs has been so far done. The first generation of the IC is SSI, that means small scale integration. The number of the components are integrated in the silicon substrate is around becoming a double in every 2 years. So therefore, the small scale integration will have the transistors from 10 to 100 transistors. The examples of the SSI is the logic gates, and we have a MSI medium scale integrations, the examples of the counters, and large scale integrations, the examples of 8-bit chip, and also here the number of the components are 1000 to 20,000. After that we have a very large scale integrations, examples of the 6-bit and 8-bit, and after that we have a ultra large scale integration which is called ULSI, that is a special processors, virtual reality machines, smart sensors and all. We all are now with the edge of the VLSI, and also in the generation of the 5th generation, which is the ultra large scale integrations. So all these the integrations of the devices have been developed every 2 years once, and making their number of the components double on their silicon substrate. This particular idea has come up from the Moore's Gordon principle, Moore-Gordon's law, and he was the co-founder of the Intel industry, VLSI industry, and he was predicted in 1947 itself. This particular integration is going to be double in every 2 years in a common silicon substrate. Still, the international silicon roadmap technology still follows the prediction of the Gordon-Moore's law as far as the latest technology concerned. So further, there is a still there is a miniaturization is still possible, because there is no end for the innovations in the devices and also the materials and also the applications point of view. There is always continuously there is a development of this VLSI. So here, over the past several years, what we have seen is the silicon CMOS technology has becoming one of the dominant fabrication process comparatively with the rest of the technologies. Because of the CMOS technology, we have a high performance of the devices, and also the cost of the devices have been reduced. So in this process, whatever the Gordon-Moore's predicted, the predicted line, which is the linear with respect to the time and also the number of the transistors per chip, and the actual growth is happened from 1960s to almost all up to 1990s, and from 1919 onwards there was a slight deviation is happened, because the actuality cannot be meet the prediction. So always the prediction, that means the theory or the model, whatever we have assumed is an ideal case, but the practicality case there should be some deviation. As far as that is concerned, almost all we are very close to the actual scenario of the prediction by Gordon-Moore's, and such a progress is highly highlighted in the recent products of the RISC chips, which is possible to process almost all around 35 million instructions per every seconds. So in this process, in order to improve on this the necessary improve the technology, one of the main important thing is the scaling, the other one is the processing. Because of the scaling, that means the size reduction, and because of the processing of the technology, the fabrications, these kind of the devices have been developed a large in scale. So therefore, and behind this, what we can say, the existing technology, that is the silicon technology, could effectively facilitate the triple of the rate. That means above of the 100 million instructions per second, one must look at the other technologies of the like a germanium arsenic, gallium arsenic based technology, which will be the most significant in this era of the ultra high speed logic and fast digital processors. So this is highly used for the high power applications comparatively, and gallium arsenic is further potential to produce the photoelectronic devices, and which is highly require the low power consumptions point of view. So in this there is a current available technologies to review their different parameters, especially the speed and power performance domains here. The graph shows the speed or the power performance of the technologies like a CMOS technology, gallium arsenic technology, NMOS technology, BiCMOS technology and ECL's technology, and the progression delay or the gate is showing on the y-axis. So here silicon based VLSI is included along with the BiCMOS, but also introduces the gallium arsenic based technology. So ECL based technology is not covered that much of the material which is relevant to the general area of the digital integrated circuits. So the potentiality of the silicon integrated circuit has been extremely rapid growth, but number of the transistors being integrated into the circuits are on a single silicon substrate, but the problem is the Moore's prediction, after prediction made by the Gordon Moore in 1960s, it is figure sets out what he has becoming known as a Moore's first law, and it says that his predictions have largely comes into the truth in the reality to increase the diversity between the prediction and actual the developments in the last almost a few years. Due to the problems are associated, the complexity and also the designing and the testing of very large scale circuits, this prediction has becoming some deviations are happened, that has the revolutionary growth for the IC technology, which is almost all in every aspect of our life we can see. And this is the table which summarizes the microelectronic evolution, how it has come from the production of the integrated circuit and also the invention of the transistor, and how IC has come and how IC has been classified by the evolutions, and what we are today utilizing the IC in our regular life. So from that we have this particular MOS transistor, that is the metal oxide semiconducting transistor, and this is the MOS transistor, the MOS technology we generally used to be say based on the PMOS, NMOS, CMOS and also BiCMOS devices. So these devices come based on their technology. Say for example CMOS technology is the complementary of the NMOS and the PMOS technology, and BiCMOS technology is a combination of the bipolar technology and also a CMOS technology. So the integrated circuit, the devices are always is adopting the new technologies, and therefore the miniaturization is happening, performance of the chip is increasing, power dissipation is improving, and also the leakage current is decreasing, and many of the device other characteristics are improving. So in this process the reasons are, although the CMOS technology is dominant technology in some of the applications where we normally use to illustrate the design process will be presented in a NMOS. The reasons are NMOS technology is a very simple, and also design methodology, design rules are easily learned, one can able to learn this, therefore this provides a very simple technology and but excellent introduction to the structure design for VLSI. So the reasons for these are maybe all these, but gallium arsenic technology have some arrangements in these relations for the development of the logic designs which are similar to these employed in a NMOS technology. So what we can say that the speed power product is measured in terms of the picojoules, and the product rate growth of the switching delay is in terms of the nanoseconds. So what we can see, the minimum line width that is showing, which is showing here are very drastically decreasing. So the CMOS transistor, what we can see, will have number of the layers, and we can see here the NMOS enhanced mode transistor, and it is the enhanced mode NMOS depletion mode transistor. In an enhanced mode transistors, the channel is created. We can see here the source in the left hand side and the drain is right hand side. The potential of the source is Vs, the potential of the drain is Vd, and between them we have a channel which is the intrinsic channel, and bottom we have a substrate which is also calling as a body, and above the channel we have a oxide layer that is made by the silicon dielectric materials, and above the dielectric material we have a metal which is the polysilicon metals, where which is provided a lead for the gate. So the source and the drain regions are formed by diffusions of the n type of the impurities, which is through the suitable mask into these areas, which will give the desired n impurities concentrations, and also it will give depletion regions, which will extend mainly in more lightly doped p regions. But the source and drains are isolated by another type of the it is something like one another by two diodes, because source and channel is having a one kind of a diode, and channel and drain is another kind of a diode. The connections to the source and the drain are made by the deposited metal layers. So in order to make a usable device of the MOS transistor, there should be always capability to establishing and controlling the current between source and the drain. For that we have two ways. One is called enhanced mode transistor, the other one is the depletion mode transistors. In the enhanced mode transistors, we have the key layers. The key layers are the metal layers, polysilicon layers, oxide layers, n diffusions, p substrate, n substrate, and also the depletion layers. So which will be providing the complete the structure of the NMOS enhanced mode transistor. And here the metal is used the polysilicon, which is deposited on the layer of the insulating over the regions between the source and drain, that is exactly over the channel. And this device is having the number of the conditions. Initially the device is when it is in initial condition where the channel is not established, where there is no channel, the device is in non-conducting conditions. In that case, the potentials of the device output potential of the device is almost all 0, because Vs is 0, Vd is 0, and Vgs is also a 0. So completely this is a non-conducting condition of the device. But if the gate is connected to a suitable positive voltage with respect to the source, what we used to say VGS, therefore the electric field will be established between the gate and substrate. The gate and substrate will be established as the electric field that gives rise to the charge inversion regions. The number of the electric charge carriers will be start flowing in the channel and under the gate insulations. So the conducting path or the channel will be formed slowly between the source and the drain. So this channel may be established, and in the present condition VGS is 0. By implementing the suitable impurities in the region between source and drain during the manufacturing process, which is prior to the deposition of the insulation and the gate, then we can have another type of the transistor, that is the depletion mode. In the depletion mode, we have a channel which is inbuilt, that is by fabrication. So the difference between the enhanced transistor and depletion type of the transistor is, in the enhanced mode transistor there is a channel will be formed slowly. Initially there was no channel, but in the depletion mode transistor the channel is inbuilt, that is by fabrication it is implanted inside. So from starting of the condition, that is VGS is 0, there was a channel inside. So under these circumstances the source and the drain connected to be conducting channel, but the channel may not be closed by applying the suitable negative voltage to the gate source in this case of the NMOS depletion mode transistors. In both the cases, what we can see, we can vary the gate voltage, which will allow the flow of the control of the charge carriers in the channel, that is from source to the drain, and current flow between the source and the drain can be controlled. So overall, in a enhanced mode and depletion mode, the NMOS technology has been applied. Therefore it was called a NMOS depletion mode and NMOS enhanced mode of the transistors. We have another type of the transistor, which is the PMOS transistor, and the PMOS transistor is made by the PMOS technology. The PMOS technology or the PMOS enhanced mode transistor is also similarly like a NMOS transistor, except the substrate is reverse. In case of the NMOS transistor, the substrate is P type of the substrate, where in case of the PMOS transistor the substrate is the N type. Remaining all R will be reverse as far as the device is concerned. So however, the applications of the negative voltage suitable magnitude between gate and source there is a formation of the channel between source and a drain here, therefore current will be current may be then flow if the drain voltage is negative with respect to the source. So, in this way the current is carried out by holes as opposite to the electrons, as in case of the NMOS flow of the electrons are the electrons. In consequences, in a PMOS transistors are inherently slower than the NMOS transistors due to because of the charge carriers are involved, and as we already know that the hole mobility is up is less and by the factor of approximately 2.5 times of the electron mobility. Therefore, these differences, the discussions of the NMOS transistor will always follow the relative equally to the PMOS transistor, but always widely used the NMOS transistors rather than the PMOS transistors.